this video, I'd like to talk about the concept of an exponent. And here I have this example, and the way that we say this is that this is 2 raised to the third power. And essentially what it means is that we want to take this number here, essentially the base, and multiply it this many times. Or in other words, if we write this out, this is just 2 multiplied 3 times. So 2 times 2 times 2. And you essentially just do it one step at a time. So we'll do 2 times 2, which is 4. And then we multiply again by 2, and we get 8. So 2 raised to the third power is equal to 8. And let me write down the different ways you can say this, because you could also say that this is 2 cubed. So you can essentially say this either way, but this first way is essentially the general pattern that we can extend to whatever base and whatever power. So with that in mind, let's start looking at different example problems. So we can start with this 4 to the third power. And again, it's just this number multiplied that many times. So let's write it as 4 times 4 times 4, since that is 4 raised to the third power. 4 times 4 is 16, and then we multiply by 4 again to get 64. So 4 to the third power is simply equal to 64. And now looking at this next example, we need an expression using an exponent that's equivalent to all these 9s multiplied together. And essentially we just want to count 1, 2, 3, 4, 5, 6, 7. So there's 9 7s multiplied together, and the shorthand for this would be 9 raised to the 7th power. Because remember, it's this number, this 9, multiplied this many times. So 9 multiplied 7 times is the same thing as 9 to the 7th. And moving on, we have 2 very typical examples here. So in the first one, we're raising 0 to the 5th power. So that's this number multiplied that many times. So it's just going to be 5 zeros multiplied together. And 0 multiplied by anything is 0. So this is just going to be 0. And over here, we have 1 to the 5th power. So it's 1 multiplied by 5 times. And if you multiply a number by 1, it's just equal to itself. So 1 times 1 is 1, and then every time you multiply it by 1, it doesn't change it. It's still going to be equal to 1. And with these two ideas, we can generalize. If I raise 0 to any positive number, then it's just going to be equal to 0. And same thing over here, if I raise 1 to any positive number, it's just going to be equal to 1. So let's now move on to our next example problem. So now it's getting a little bit more difficult. We have this 0.2 raised to the 4th power. So it's this number multiplied that many times. So we have this 0.2 multiplied 4 different times. And you can either use a calculator to evaluate this, or we can just multiply 2 4 times and then move the decimal 4 places. So this would be 16. So then when we're doing this problem, we're just going to take our 16 and move the decimal 4 places. And we'll have to fill in 2 zeros there. So 0.2 to the 4th is simply equal to 0.0016. And below that, you have this 1/3 to the 3rd power. So the pattern is just going to follow just like before. We have this number multiplied this many times. So rewrite it as 1/3 times 1/3 times 1/3. And when you're multiplying fractions, you just go straight across in the numerator and straight across in the denominator. So in the numerator, we have 1 times 1 times 1, which is just 1. And in the denominator, we have 3 times 3 times 3, which is 27. Or you could think of it as 1 over 3 cubed. And with this type of problem, we can essentially notice a pattern. So let me look at the example. Let's say 2/3 to the 4th power. So essentially, we're just multiplying that 2/3 4 different times. And again, we're just going to multiply straight across in the numerators and the denominators. So in the numerator, you have 4 2's multiplied together. So we could write that as 2 to the 4th. And in the denominator, you have 3 3's multiplied together. So we could write that as 3 to the 4th. And in general, if you have some fraction, a over b, raised to some power, x in this case, that power essentially distributes to both the numerator and the denominator. So in this case, it would be a to the x divided by b to the x. So we can look at a very specific example, like if we had, let's say, 6 over 13 raised to the 12th power, then we know that we're essentially just multiplying 6 by itself in the numerator 12 times. So we have 6 to the 12th in the numerator. And in the denominator, we have 13 multiplied by itself 12 times. So this would be 13 to the 12th power. And in the next video, we're going to consider negative exponents. So what if we had something like 2 to the minus 3 or 4 to the minus 7? How do you deal with this?